There are a lot of people say, well, I'm not going to worry about a magnitude 8.5 because that's what's called a 500-year earthquake. Well, that means in 500 years you have a 100% chance that that earthquake is going to get you. But it means also that in 50 years you have a 10% chance.
In our lifetimes, we are going to see the magnitude 7, magnitude 8. We're going to see magnitude 7 events here. So it's definitely important to prepare for it.
It's not if a large earthquake is going to hit the west coast of the United States, it's when.
We're helping to make one of the coolest buildings in LA and maybe the world withstand the next earthquake. The theme building at LAX is a wonderful slice in architectural history.
It's an icon for Los Angeles. When you land at the airport, you realize, wow, you're in LA, you're not anywhere else.
It's really the brand of Los Angeles.
It's an iconic project.
Like most buildings built in the 50s and 60s, it is not ready for as big an earthquake shaking as we now know can happen. It needed help.
Conventional retrofit strategy would have altered the appearance and changed the look dramatically.
The challenge comes in applying modern earthquake protection technology to an historic building while not changing the way it looks.
You cannot do anything to the structure, but somehow make it better. That's a challenge.
A non-creative engineer would have just put more concrete and steel on the outside of the building and made it stronger.
It would ruin its appearance. It would be very costly and very time-consuming.
Would not have been the theme building any longer.
That's really what led to using a tune mass damper.
This is the mass damper. We put the 1.2 million pounds on top of this building.
Those people had a rather radical idea.
It was unique because the building was unique.
The unique solution is to take 1.2 million pounds of steel and put it on top of the building. Normally in earthquake engineering, that's stupid.
As an engineer, you're always taught that the more weight you put on the building, the worse it is. And then when our consultants tell us we want to add 20% of the weight of the building and stick it on the very top, but are you guys serious?
The idea really came to us from Kit. It was an unusual idea, but once he proposed the idea to us, it suddenly sounded right.
The way I describe the tune mass damper is we put 1.2 million pounds on 8 rubber bearings. DIS manufactured the rubber bearings. The rubber bearings help control the movement of the 1.2 million pounds. Then there's 8 shock absorbers, or fluid viscous dampers, made by Taylor Devices. As the tune mass damper moves, those 8 shock absorbers absorb the energy of that movement. The 1.2 million pounds counteracts the earthquake motion.
It acts as a counterweight. So if this building going to shake that direction, the whole mass going the other direction to dissipate the energy down there.
So the ground is trying to shake the building, and the building moves at a particular frequency, and you make sure that at the same frequency you have a mass that opposes the building as it tries to move back and forth. You hold it back.
We're trying to modify the structure's behavior, make the mass move during an earthquake and the building move a lot less.
So the tune mass damper solution is a much quicker solution and a much less costly solution.
It was a very innovative solution that would have minimal impact on the architecture.
We found the best solution for this building. We were asked to construct something that had never been constructed before using a tune mass damper in a seismic application.
I looked at the structure, I looked at the existing conditions of it, and I personally thought it was going to be more of a challenge than it actually was.
It's going to be interesting. I've never seen it, so this is going to be an interesting project. 22 layers, 6 plates each, which is 132 plates. When all is said and done, the TMD will weigh 1.2 million pounds.
There's 132 bolts that got to line up in less than a 16th of an inch. Once we get all of them lined up, we'll weld the plates together, then we'll start setting the second layer on top. Weld all the seams, grind them smooth, and then do it 22 more times.
If one fits, they all fit. And so when we pulled up the first plate, it's a relief to know that it fits, because now we know that all of them will fit.
TMD is in place. They're putting the 164 through bolts in it to cinch it all together now. They're probably welding those last seams as we're speaking, and
We can start stacking the roof on this next week.
We're simulating an earthquake. This is a little shaker that produces about 10,000 pounds of force. It's enough to move the building noticeably. The only way they could have to predict what would happen when they stuck that tune mass damper up there is in the computer. And so what we're doing now is providing ground truth, is where we're measuring what's actually happened. And it's actually pretty close. For a structure this complex, it's within a few percent of what their models predicted. Bottom line is that the retrofit that has the main feature of the retrofit, the TMD, works as advertised.
Well, today we're announcing the reopening of the observation deck at LAX.
It's been a long road. It's been very enjoyable.
Everything came together, it's built, and it works.
There was an incredibly creative team in coming up with and accepting a methodology for doing this that's unique.
A legacy, something that I will always have as part of me.
We feel like we're pushing the boundaries of earthquake engineering.
See, earthquake engineering, earthquake structural engineers, we make it or break it for society.